So now we continue with the numericals based on the power circle equations. Only based on the equations whatever you have derived there. But this is asked in one of the GATE question papers. So you are having two buses, bus 1 and bus 2. You treat like bus 1 as the sending end and bus 2 as the receiving end, and check what is the power transmitted from bus 1 to bus 2, that is from sending end to receiving end of a transmission line. So we have to find out what is PS and what is QS here. Anyway, we have derived this one. How much here? dVs square by B cos beta minus alpha minus Vs Vr by B cos of beta plus delta. And what is the value of D here? 1. ABCD mentioned, by default you write the values. How much the voltages are? 100. Reactance, how much? The magnitude is 5. J5. And what about beta? If it is 0 plus J5, beta is tan inverse 5 by 0, 90 degrees. Alpha is 0. Next we have 100, 100. B is 5. Beta is 90. What about delta now? Bus 2 voltage 100 at angle 0. Bus 1 voltage 100 at angle 30. So simplify this one and find out what is PS. On simplifying you get it as 1000 watts. Now what is QS? It is sin beta minus alpha. Again we have Vs Vr by B sin beta plus delta. So same values, but you express in terms of sin now. So what is the value of QS now? You get 268 VAR. What is the angle you get now? What is the magnitude you get? It is 268 volt amperes reactive. So simple calculation based on substitution of data in the formula and find out what is PS and QS. Now we begin with the next topic, power system stability analysis. Power system stability analysis. First we discuss three conditions and then you define what is the power system stability. So in condition 1, you consider an alternator, step-up transformer, transmission line, further step-down transformer, further you connect some load. Which type of machine we are having? Synchronous generator. And here we are having transmission line. Now the question is this single line diagram associated with power system stability? So when you say it is associated with power system stability, for that you check the source. At the source we have a synchronous machine. So this single line diagram deals with power system stability. Deals with power system stability. And now we have the condition 2. Step up transformer, step down transformer, load here. Now we are having a synchronous machine. So which type of load here? Asynchronous load. What do you mean by asynchronous load? Electrical heaters, induction motors are few examples of asynchronous load. Now what about this second single line diagram? Is it associated with stability? For that you check the source. At the source we have asynchronous machine. So this single line diagram is not associated with stability. Is not associated with stability. Now we check the condition 3. You have synchronous motor, but here asynchronous machine, here transmission line. Now is this single line diagram associated with stability? Check the source. We have asynchronous machine. So asynchronous machine, So it is not associated with stability. This is not associated with stability. So to check the stability, you check the source. If we have a synchronous machine at the source, then the single line diagram deals with stability. Then the single line diagram deals with stability. Now we define the power system stability. It is a property of synchronous machine. Which property? To transmit maximum active power from source to load. To transmit maximum active power from source to load. By maintaining synchronism with this externally connected transmission line. So it is the property of synchronous machine to transmit maximum active power through the line by maintaining synchronism with externally connected transmission line. You define as stable power system stability. So we come across the definition. It is the property of a synchronous machine to transmit maximum active power to the load through transmission line by maintaining synchronism with externally connected transmission lines. This is the definition of power system stability. Now we check the conditions when a power system network is operating under stable conditions. So when a power system network is operating under stable condition, first one is, you say that rotor rotates at omega s. Are you right? N equal to ns. So what is the meaning of this one? The meaning of this one is rotor neither accelerates nor decelerates. Then what is the accelerating power? Mechanical input PS minus electrical output is 0. For a synchronous generator, input is mechanical PS, shaft input. Output is electrical P. So what about PA now? 0. And what about delta now? We have stator axis and here rotor axis. What is the angle now? Delta. When the system is operating under stable conditions, what about delta? Delta remains constant. You say that the delta remains constant. So these are the conditions you get for stable power system network. Now we check the classification of power system stability. There are two classifications. First one is the steady state stability and other one is transient stability. So what is the steady state stability? Why it occurs? Due to the changes in consumer load. Why you get the changes in transient stability? Why you get the transient stability? Due to the short circuits or faults. Now due to changes in consumer load, you say that the changes in the load demand are small and gradual. So you say steady state stability, the changes in the load demand are small and gradual. What about here now? The changes in the load demand are sudden and fast, or you say sudden and large. As the changes in the load demand are small and gradual, the frequency of rotor is less than the supply frequency. As the changes in the load demand are high, frequency of the rotor exceeds the supply frequency. Exceeds the supply frequency. So now you define the steady state stability. How to define steady state stability? So just continuation of this definition only. First three lines are as it is, but what we include at the end, we mentioned that for small and gradual changes in load demand. For small and gradual changes in load demand. This is how you define power system stability. The steady state stability is the property of synchronous machine to transmit maximum active power to the load through transmission line by maintaining synchronism with externally connected transmission lines for small and gradual changes in the load demand. Now, how to analyze steady state stability? There are different methods. The first method is we develop the static model for the given power system network. Static model means independent of time for a given power system network. So now you analyze steady state stability. Analysis of steady state stability. The first method to analyze the steady state stability is static model. So in the static model, you consider an alternator connected to a load directly. And say now, so you consider an alternator connected to the load directly. And what about the reactance of the alternator? You can represent alternator E at angle delta, load V at angle 0. So how you draw its reactance diagram? This E at angle delta, reactance Jx, and here the terminal voltage V at angle 0. Say current flowing is I per unit. So you are neglecting the resistance place. So R very much less than Jx. So what is the current flowing from source to load now? The difference in potentials divided by the reactance is Jx. So E at angle delta minus V at angle this one, X at angle 90. So how much you get? E by X delta minus 90, V by X minus 90. Now how you find what is the complex power S? It is V I conjugate. So V at angle 0, I conjugate, how you write? E by X 90 minus delta V by X plus 90. So how much you get now? EV by X angle 90 minus delta minus V square by X plus 90. So from this, how you find what is the active power? So electrical power output PE, how you write? Assign cos for this one. Cos 90 minus delta V square by X cos 90. Cos 90 is 0. So you get EV by X how much? Sin delta. This is the formula to find the electrical output power. So when you draw a curve with PE along y-axis and delta along x-axis, what do you get here? It is a function of sine. You get as the sine function like this. So what will be this one? PE maximum. When it will be maximum? When delta is 90 degrees. So you can observe here, at delta 90 degrees, what about this PE becomes PE max? What will be that PE max now? You have EV by X sin 90. So how much you get now? It is EV by X. And what you call this maximum power transmitted? Steady state stability limit. So how you define the steady state stability limit? Maximum active power transmitted from sending end to receiving end of a transmission line by maintaining synchronism with externally connected transmission line for small and gradual changes in load demand, and when it is possible at delta equal to 90 degrees. Maximum power is transmitted You name it as steady state stability limit. So this is how you define steady state stability limit now. So how you define the steady state stability limit? It is the maximum active power transmitted through the transmission line from sending end to the receiving end by maintaining synchronism with externally connected transmission line when for small and gradual changes in the load demand. So this is the method 1. Now we have the method 2, which you name it as synchronizing power. That is the degree of magnetic coupling between the stator axis and rotor axis. You name it as synchronizing power. So what about this synchronizing power? It deals with the degree of magnetic coupling between the rotor axis and stator axis. Mathematically, how you find this synchronizing power? It is dPe by d delta. How much you get? You get EV by x. Sine derivative is cos. The derivative of sine is cos. So this is the formula to find out the synchronizing power. Now we consider different cases. First we assume that rotor air gap flux is magnetized. We assume that the rotor air gap flux is magnetized. So what is the value of delta? Greater than 90 degrees. If delta is greater than 90 degrees, what is the synchronizing power? Cos more than 90 is negative. So what about the synchronizing power? The synchronizing power is negative. Synchronizing power is negative. Then what about the case 2 now? So here it is demagnetized place. Case 1. Now the case 2, the rotor air gap flux is magnetized. For this condition, what is the value of delta? Less than 90. Then what is the synchronizing power? Cos less than 90, it is positive. If synchronizing power is negative, what about the system unstable? Synchronizing power positive. What about the system? Stable. So you can also represent that synchronizing power here. Represent delta. Here dPe by d delta. So delta 0, how much you get? EV by X. Delta 90, 0. Delta 180, it is negative. So these are the values you get. That is the curve of synchronizing power. This is the curve related to synchronizing power. So when the system is unstable, when delta exceeds 90 degrees, so you refer power system stability as angle stability, because up to delta 90 degrees system is stable. Beyond 90 degrees the system is unstable. So you refer power system stability as angle stability. You name it as a angle stability. So this is the method of analyzing the power system stability. Now the method 3 is using ABCD constants. Now further we have method 3. What is that method 3? Using ABCD constants. So represent a transmission line using ABCD constants. Now what about the sending end? We represent Vs at angle delta. What about receiving end? Vr at angle 0. Already you have derived the formula for active power transmitted. What is the formula? Vs Vr by B cos beta minus delta minus AVR square by B cos beta minus alpha. Now we implement this formula initially for short transmission line and further for a long transmission line. So for a short transmission line, what are the parameters? A is 1, alpha equal to 0 degrees, so now we substitute these values now. Vs Vr by B. B is the impedance. What is the impedance of a line? R plus jXL. So what is the magnitude? B gives the impedance under root R square plus XL square. So X component R, Y component XL, phase angle is now what it is? Beta. So what is the value of tan beta here? It is XL by R. So Vs Vr by B cos beta minus delta A is 1, Vr square by B, here you mention only cos beta. So this is the electrical power transmitted. Now, when this PE becomes PE max, when beta equal to delta. So if you say now, the impedance phase angle beta equal to delta, then what about PE becomes PE max? So what about that PE max now? We write Vs VR by B cos 0 1 minus how much? VR square by B, how much cos beta? R by Z. So on simplifying this, what you get? B is under root R square plus XL square. B how much? Under root R square plus XL square. Z is R square plus XL square. Now we have to check what should be the value of the reactance of the line so that the maximum power is delivered. For that, what you do is you differentiate this equation with respect to S and equate to 0. How much you get that XL? You get it as root 3 into R. So what will be tan beta or beta now? Tan inverse XL by R. Tan 60, you get it as 90 degrees. Or that is nothing but delta. You know, for maximum power to be transmitted, beta is same as delta only. So how much that value is equal to 90 degrees. So to transmit maximum power through a short transmission line, what should be the load angle? Delta 60 degrees. Important point. So through a short transmission line, when the maximum power is transmitted for delta equal to 90 degrees, 60 degrees. If delta equal to 60 degrees, then maximum power is transmitted through a short transmission line. Now what about that beta in case of a long transmission line? What about that beta in case of long transmission line? You can verify now by this analysis. You know that long transmission line, the power transmission capacity increases. So when you can transmit more power, when size of the conductor is high. So for that, the size of the conductor is high. Or you say, the area of the conductor is high. So if area is high, what about the resistance? Decreases. If resistance decreases, what about beta now? If this resistance decreases, beta definitely increases. So it's nothing but increase in beta, nothing but increase in delta for maximum power to be transmitted. So you check this sequence of steps. For maximum power to be transmitted through long line, as beta should increase, delta should also increase. But what happens if delta increases beyond 90 degrees? The system becomes unstable. So if delta exceeds 90 degrees, already we have discussed, then what about our system becomes unstable. So ensuring the stability, how to ensure that delta do not increase 90 degrees, ensuring stability, how to make sure that delta do not exceed 90 degrees. For that, observe the alternative here. So beta is tan inverse XL by R. Now you want beta to be constant, but R is increased. So what you will do now? R value is decreased. As R decreases, beta increases, R decreases, beta increases. So accordingly delta also increases. If delta exceeds 90 degrees, then system becomes unstable. But you want that beta or delta to be constant. So in the process of transmitting more power, R decreases. So decrease XL also. So what you do? You decrease the reactance also. Then how to decrease the reactance? So we have a transmission line, has its own reactance JXL. Now in the transmission line, you connect a capacitor in series. So what is the capacitive reactance? We say minus JXC. So what will be the net reactance now? Add this JXL plus minus JXC. Adding this to how much you get? XL minus XC. So previously only XL. Now XL minus XC, the reactance is decreased. So decrease the reactance to the extent resistance is decreased. Thereby you can maintain that beta or delta constant. Beta or delta constant, or you ensure that delta do not exceed 90 degrees. So by connecting a capacitor in series with transmission line, you are ensuring that delta do not exceed 90 degrees. What you call this method as series compensation. So what is series compensation? Connect a capacitor in series with the line. What for? So that the net reactance decreases. Say decrease it to extent R has also decreased, and mention that delta or beta constant and ensure that delta or beta do not exceed 90 degrees. So this method you call it as what? The series compensation. So ensuring delta not exceeding 90 degrees by connecting a capacitor in series with the transmission line. Capacitor in series with the transmission line. So therefore what happens? The net reactance decreases, delta is made not to exceed 90 degrees. Delta is made not to exceed 90 degrees. So this is the method, you name it as series compensation. Now you have 5 minutes break. First question is by Vishwam from Agartala. Why we check stability for synchronous machines only? The concept of stability deals with the source, and what we have at the source, either a synchronous machine or asynchronous machine. Further, you know, around 99% of power system network is transmission line. Even though you have a synchronous machine at the source, you can transmit power. But it definitely results with unstable conditions. Because for non-synchronous machines, you cannot achieve the stable condition, that is PA equal to 0 cannot be achieved. So always we check stability for synchronous machines. Next question is by Vishwam. The steady state power is maximum at rotor angle 90 degrees. This is achieved by assuming line to be fully inductive only. Practically we have resistance, then rotor angle will be less than or greater than 90 for maximum power transmission. Now you know that for maximum power to be transferred, impedance phase angle beta equal to tan inverse XL by R, that is delta. So how much the delta must be? For a short transmission line, to transmit maximum power, delta equal to 60 degrees. And for long transmission line, delta increases, but don't exceed that delta beyond 90 degrees. Otherwise system becomes unstable. And the delta 90 degrees has nothing to do with a fully inductive line place, no relation in those aspects. Delta 90 is the maximum value or a critical load angle for maintaining stability for a given power system network. So for long line we make that delta not to exceed 90 degrees by connecting a capacitor in series, that is series compensation technique.